In this video, we're going to talk about the chi-square test of independence. These chi-square tests that we have been discussing are relevant particularly for categorical variables. And the chi-square goodness of fit test is dealing with one categorical variable with multiple categories usually. But here, with the test of independence, we are going to compare two categorical variables, and namely if there is a measurable association or independence between the two of them. Typically, the way that this information is presented is in a table. This is a contingency table. We've seen this before back in our probability section of our course. Here, usually the letter R is representing the number of rows in this table, and K would be the number of columns. And so the rows and the columns are representing the number of categories for each of the variables represented in the table. So I think one of the best ways to go about explaining the test of independence is just to clock into an example. Here we go. In this study, there was a total of 300 rats that were randomly selected from a distributor of rats and randomly assigned to one of three treatments. They were receiving different carcinogen dosages here. We had a control group, you know what that means, a low dose and a high dose group. And then they tracked the number of tumors, if tumors developed, in each of those poor 300 rats. So, is there statistically verifiable correlation between the dosage level and whether or not a rat developed tumors? Before we go crunching numbers and defining our null and alternative hypothesis, let's just consider the type of data that is presented here. Right, there are two categorical variables. We've got the dosage amount, right? And there's three categories in that variable. And then there are whether or not tumors were developed. So we've got no tumors or at least one tumor. So there are two categorical variables here, and they are measured within one sample, right? There's one sample of 300 rats, and two categorical variables were measured. So that would be an indicator here that we need to use this type of test. Let's define the null and alternative hypotheses for this chi-square test for independence. We're testing if there is an association between our two variables, the dosage level and the tumor incidence. Okay. As we know, the null hypothesis is always a statement in some way of no change or no difference. Here we're not talking about means or standard deviations, but in terms of a relationship between these two categorical variables. So here I'm going to mention that the two variables, tumor incidence and dosage amount, that there is no association between them. I'll say is independent of each other. So another way to think about that is there is no association. For every test we've done, the null hypothesis is always about some statement that there is no change or no connection really between the groups being compared. The alternative hypothesis needs to say the opposite here. So I will state that the tumor incidence is not independent of dosage amount. Or in other words, that there is an association between our two categorical variables. As usual, our next step in the hypothesis testing framework is to determine the test statistic. Just like with the goodness of fit test, we're going to need to determine some expected values for each of these cells. And before we do that, however, it's going to be useful to have the marginal totals for each row and for each column. So let's do that here. Adding up the number of rats who experienced at least one tumor. That looks like a 44. The number of rats that did not, 256. Then the total number of rats in the control group appears to be 100. I'll use a separate color. 95 in the low dose group and 105. And of course, adding up this column total, all the marginal totals here, we get the sample size of 300. We're going to need these totals to help us determine the expected values for this test. Remember that an expected value in a chi-square test is the number of rats expected to have obtained a tumor if the null hypothesis is true. If there really is no association between tumor incidence and the dosage amount. And then we'll do the expected number of rats to obtain no tumors if these two variables are not associated. So there's actually 6 expected values that need to be determined, and we'll do 3 at first, and then we'll do 3 more. You'll see why. But remember the formula for expected values. It is simply n times p. N times p. In this case, however, the n and the p are both going to fluctuate depending on what dosage group we are considering and the probability of obtaining a tumor under the assumption of the null hypothesis. Let's start with the p. What is p going to be? Well, this is the probability of obtaining a tumor. Tumor occurs given that the null hypothesis is true. If the null hypothesis were true, then we would expect the same probability of obtaining a tumor, regardless if you are in the control group, low dose, or high dose group. So essentially, the dosage amount doesn't matter. Let's put all the rats who got a tumor in one group, and we can see up here that that total is 44 rats that obtain a tumor out of the 300 rats total. So it doesn't matter the dosage amount if these two variables are independent under the null hypothesis. So we're going to use this quantity for all of the p's here. Okay, well, what will n be? The n is the number of rats in each of these groups. So we have the number of rats in the control group. You can rewind and see that that was 100. The number of rats in the low dose group was 95, and 105 in the high dose group. So those are the n's for each of these groups. And now we'll multiply by the p under the assumption that the null is true. Okay, so performing that simple multiplication, we're going to result in decimal values. That is okay. Just keep those like they are. Quick recap here before we do this again. This is the probability of observing a tumor in a rat if it doesn't matter what group you're in. Since there was 100 rats in the control group, we would have expected about 14.6 of them to have obtained a tumor if there truly was no effect of the dosage amount. So hopefully that helps. So we are halfway there. We're going to determine the expected values for the other 3 cells up here. The process is going to be the same, except now this is going to be for the column that has no tumor occurring. So again, we need to do n times p for all of these. As we saw earlier, the n is going to fluctuate and the p is going to be different from the previous set up here. P is the probability of no tumor occurring, again under the assumption that the null hypothesis is true. So out of the 300 rats, how many of them obtained a tumor? Well, that was the 256. So that is going to be the p for all of these. The n is, again, the number of rats in the control group, in the low dose group, and the high dose group. We will multiply by this probability here. Okay, so calculating these expected values now is going to allow us to create the test statistic. Because this is a chi-square test, we need to compare the observed number of individuals in each of these categories. So that was the given data. And I think it's quite nice to rewrite all of these expected values sort of in a matching format in this table, just so you know which observed values need to be compared to which expected values. For instance, this 14.6 is the expected number of rats to have obtained tumors in the control group. So obtained tumors, control group, 14.66666. And 13.93 will be right below it, etc. This is just going to be handy for when we compute the test statistic. So we can make a direct comparison between the observed and expected quantities. Before we go crunching our test statistic, I know that this framework for determining the expected values here may have seemed a little convoluted. I wanted to show you the why, but here is a shortcut. In general, the expected values for each cell in a contingency table can be determined by the following shortcut formula. It is the row total for a cell multiplied by the column total and divide by the total, the sample size. Now let's just validate that real quick. This 89.6, let's look at that. The cell on the bottom right refers to the number of individuals in the high dose group who did not experience any tumors. So what is the total of that row? Well, we saw that that was 105. And what is the total of that column? We saw that that was 256. So just a quick check here, 105 times 256 divided by n 300, and just check that those are the same amounts within this product here. So this little shortcut formula can save you a lot of time, so you don't have to consider all the elements necessarily in the expected values. But I did want to show you that there is some rhyme or reason to this formula. Okay, we are ready finally to compute the test statistic for this chi-square test for independence. I have our expected and observed values, and here is our formula for the test statistic. It is the same formula that we saw for the goodness of fit test. Okay, let's start with the first column and we'll go downwards, and then we'll go to the second column, we'll go downwards. So there were 10 rats who obtained a tumor in the control group, but 14.66666 were expected if dosage really didn't matter over that expected amount. Next up, 14 in the low dose group who got a tumor, but 13.93 were expected. Okay. 20 rats got a tumor in the high dose group if there really was no effect of dosage, then 15.4 were expected. Okay, now I'm going to go to the top right here. Lastly, 85 rats obtained no tumor in the high dose group. If there was no effect of dosage, we would have expected 89.6. Okay, so put that in your calculator and smoke it, and you get about 3.35 as our test statistic. Next step is to determine the p-value for this hypothesis test. Recall with chi-square tests, this is a right-skewed distribution, and we need the degrees of freedom. We'll talk about that in a moment. But we are finding the area to the right of 3.35. So what is the degrees of freedom for this test? Remember, for the goodness of fit test, it was just categories minus 1. Here, we want to do that as well, except we have 2 categorical variables. So it is the number of rows minus 1 and the number of columns minus 1. In this case, we had 3 rows, we had 3 dosage amounts, and then we tracked if a tumor was observed or not. There was 2 columns. As you can see, this is a 2. So our degrees of freedom here is 2 for the chi-square distribution. We want to find this probability, that is our p-value. In R, we are seeking a probability for the chi-square distribution. we need p chi-square. Our chi-squared test statistic value, about 3.35, comma, degrees of freedom is a 2. Now this is going to give us the area to the left of our test statistic, but we want the probability of observing this result or greater to the right. We must 1 minus. Our p-value is therefore about 0.1873. Next step is to state our conclusion to the hypothesis test. At the 5% level of significance, our p-value exceeds alpha. Therefore, we do not reject the null hypothesis. As usual, I like to take this very technical statistical terminology conclusion and translate it back into what this study was all about. Here, we are stating a conclusion based on sample data. Because we are not rejecting the null hypothesis, the data does not provide evidence for the alternative hypothesis, which states that there is an association between our two variables, the tumor incidence and the carcinogen dosage. This may be contrary to maybe your preconceived notions, but as scientists, we need to be open to alternative viewpoints, and if this data was obtained in a sound fashion, then this is what the data is suggesting. Remember, this doesn't prove that there is no relationship between tumor incidence and carcinogens. Pardon my typo. It just suggests that based on this data alone, we are not seeing this association. One last element we need to discuss are the requirements for this chi-square test for independence. Because it's a chi-square test, we need all the expected values to be at least 5. And we can kind of take a glimpse of them up here in the test statistic. The smallest one was 13.93, so yes, that was met. Check. And because we are making inferences to populations based on samples, of course, we need random sampling or random assignment. Random assignment or sampling. I believe random assignment was mentioned in the start of this video. If we scroll up, we see that the 300 rats were randomly selected and randomly assigned to the 3 treatments. So this was a complete randomized design. How would we have executed this chi-square test for independence in R? Well, here I have entered the data frame in. Data frame is called rats, and it matches, if you want to rewind and check, all the rows and columns are in agreement. Well, just like the goodness of fit test, the function is actually the same. chi-sc.test. Now, what about the input? Remember, in the goodness of fit test, we needed the observed data. And so I'm actually just doing a little review here. and then P equals a vector of proportions. That's fundamentally different from what we are doing here with the test for independence, because we've got two variables to input that are organized in this contingency table. So we actually just enter the data frame. However, this data frame is going to include this text vector, and we would be met with an error of some sort because R is unable to perform computations with the vector called dosage group. So I actually need to limit the input here. Remember, we use those hard brackets to refer to a specific subset of a vector or data frame. And I want to use all the rows, row 1, row 2, and row 3, right? We've got data in all 3 rows. However, I do not want to use the first column. So I'm going to leave a space here. I don't actually need the space. I'm going to leave an empty entry before the comma, indicating that I want to use all 3 rows. But I only want to use the columns, the second and the third column, 2 through 3. So now the input here is still a data frame. We're just ignoring this first column because R doesn't know how to work with that here. Now when we perform this test, we should see our p-value match what we did up here. And we should also see our test statistic match our previous work. Here it is, our chi-square test statistic, 3.35, which matches what we did earlier, degrees of freedom 2, in agreement, and our p-value from the chi-square dot test function matches our manual p-value up there. We also saw in the goodness of fit video that we can request from R the expected values of this test if we use that same input from before and $expected. What we should see here is the expected values that we computed earlier, also in that tabular format that we replicated as well. The next video, we are going to discuss what happens when this requirement of the expected values are not met. See you there.